So these are additional examples for formal definition of a limit. So we have seen the solutions or the proofs for the following numbers from 1 to 5. Now let's look at an example involving quadratic functions. So prove using the formal definition of a limit that limit of x squared as x approaches 3 is equal to 9. So there are too many details on how to go about the proof of this one here. So it's a bit different, or there are a lot of um, modification that you just need to do compared to proving the limit when it comes to linear function. So for one, we'll relabel, or we'll start, instead of using the word proof at this early point, we'll label it first as patchwork and still start with let epsilon to be positive. Now, we still start with your familiar familiar inequality, which is f of x minus the limit L, so x squared minus 9. If x minus 3 is our absolute value of x minus 3 is greater than 0 but less than delta. Now, we factor x squared minus 10 as x minus 3 times x plus 3 less than epsilon if the same condition, and then we factor out x minus 3. When we use the property of absolute value to obtain absolute value of x minus 3 times absolute value of x less than epsilon if we satisfy this condition. Now, here's the problem. Unlike in the linear function, we are able to extract x minus 3, basically the domain, and there would be no variable involved here. You might be tempted to say, well, why not consider epsilon over x plus 3, which is our delta? You see, delta only has to depend on epsilon. It cannot depend on x. If that would be the case, it means that if your x is far away from -3 or close enough to 3, it would affect your choice of delta. What should only affect the choice of delta would be the value of 9, or how put this way, the only thing that should affect delta would be epsilon, and epsilon is related to the distance of 9 from x squared. Delta shouldn't depend on where x is situated. Okay, so what we do here is, let's choose some initial value to use the restriction for delta, and say we always choose the value of 1. That is, delta is less than 1. Now, why should we choose 1? Remember, delta here is the length of the interval, or the length of the interval wherein 3, or x is a distance, or delta is the distance of x from 3. And 1 here, the reason why we choose 1 is because of the unit line, 0 to 1. For in terms of calculus, this one is already a big interval, or it's a sufficient interval wherein it's a big enough interval wherein we can talk about the limit of a function. Anything beyond that one, well, perhaps the limit or the value of x squared away from 9 becomes bigger. Okay, so we want it to be sufficiently small. This is another way of saying sufficiently small. Delta is less than 1. So notice we have a footnote here, a scratch work inside a scratch work, this pink one. So what we do is we take this one here. We're going to modify it for the meantime. So we have this condition or hypothesis, and we want delta to be less than 1. What it means is this part here, by transitivity, this one would be less than 1. And then we use the the property of this absolute value. If the absolute value of x minus 3 is less than 1, it means x minus 3 is less than -1 and 1. Notice the arrows here. This or this follows from this, but not the other way around. Okay, but this is equivalent to this statement. So what this means is equivalent. And then what our goal is to extract this one out. It's the same from this one. Initially, we want to extract x minus 3 from this one here. For now, so there are two things that we are extracting. We are extracting x minus 3 out of this, and we are extracting x plus 3 out of this. Okay. So anyway, let's just avoid convolution too much. The point is we want to obtain this from this and this from this. How to put this way? You want to extract x minus 3. Okay, you want x minus 3 would be found here, but x plus 3 would be found also here. Yeah, that's okay. That should be the arrow. So what we do here is we add plus 3. Of course, if we add plus 3, we have to subtract 3 in order to preserve the inequality, or better yet, the equality of this one. X minus 3 is equal to x plus 3 minus 3 minus 3. So this is our goal here. So you see here, we now obtain x plus 3, and then we just add -3 and -3, so we get here -6. Then we transpose -6 to both sides, we get here x plus 3 is less than 5 and 7. But it also means that what we're going to do is between 5 and 7, pick the bigger one. Now, the idea here is you want the most number of x's, or the most number of x's that has distance from -3, or better yet, the most number of x's whose distance is from 3. So there are more x's if this will be the interval that you're going to choose versus -5, x plus 3, 5. There are more numbers in this one here. And this would be equivalent to this absolute value. So we go back to our scratch work. So we have this one here, and this is the condition. Now we can replace this absolute value by less than 7. So this one here is less than 7. So this is less than this. If we now have this additional condition. And with that, we're able to provide this inequality. Okay. So we'll also let delta to be equal to epsilon over 7. So we now have our formal proof. Now the formal proof is this is not the part that we're going to formalize whatever we have written in this scratch part. So let epsilon be equal to delta, let epsilon be positive, and let delta be equal to the minimum between epsilon over 7, comma 1. Now, why is it minimum if we have just talked about admitting the most number of x's? Well, that's correct. We want to admit the most number of x's in the smallest space. That's the idea. Remember, delta here is an interval. So there are more numbers in your interval. You want that property. There are a lot of numbers in an interval. And with that much number that you obtain, basically it means there are many numbers approaching 3. This limit is further justified, or it is further refined the more numbers you take. There are more numbers you take in a small, this is what I mean, in a small space. So here is the first line of your argument. So what we do, it's still true that absolute value of x minus is greater than 0 but less than delta. We choose here first 1. So it means delta can take at least two values. So for the first value, it's this first inequality, which is the first restriction. Then it's just a matter of formalizing what we had written in our scratch work. Then this absolute value of x minus 3 is less than 1, which is the same as this, which is the same as this. It's the same computation, we're just rewriting it, and this follows too, which is equivalent to x plus absolute value of x plus 3 is less than 7. And notice I've changed the colors. You have here green and the blue. We'll make use of these colors later on to explain or to elucidate the inequalities. Now, after we take care of this delta here, now we choose epsilon over 7. So if delta is epsilon over 7, then absolute value of x minus 3 is less than epsilon over 7 because of this inequality. And then instead of doing this instead of using the concept, the definition of this absolute value, we just cross multiply. And upon cross multiplying, we're going to combine these two here. By combining, it means I'm going to multiply x minus 3 to both sides. So to the left-hand side and the right-hand side. I mean, you can do so because absolute value of x minus 3 is positive. So it's very safe. Now you know why there's a positive here. And there's no equality. So because if there's equality, then there should be an equal sign that belongs here. So absolute value of x minus 3, absolute value of x minus 3. So we get this inequality here. Basically, you're just combining these two. And because 7 times absolute value of x minus 3 is less than epsilon, what happens is this one is less than epsilon. And then just multiply them all together, you get this one. Absolute value of x squared minus 9 is less than epsilon. And therefore, we have proved what we want to show. Okay. Using the formal definition of a limit, prove that the limit of x squared minus 4 as x approaches -2 is equal to 0. We proceed in the same way. Scratch work, let epsilon to be equal, let epsilon be positive. The absolute value of x squared minus 4 minus 0 is less than epsilon if x minus -2 is greater than 0 but less than delta. Sorry, there's an absolute value. And we simplify this one. Absolute value of x plus 2 is less than 0, less than delta. Then we can factor this. X minus 2 times x plus 2 is less than epsilon, which is equal, or which is the same as absolute value of x minus 2 times absolute value of x plus 2 is less than epsilon. We again arrive at the same problem. So we restrict delta to be less than 1. So copying this condition, 0 is less than absolute value of x plus 2 is less than delta, less than 1, which is the same as this. So take this into inequalities. By definition, x plus 2 is less than -1 but greater than 1. And then we want to extract this absolute value. So we add -2 and +2. So this cancels out and just obtain this original one. And then this is the +2. And then we combine these two here, x minus 2 plus 4. And then adding 4 or -4 to both left and right hand side. So we get here, oops. So it should be -5 and, sorry, 4, so this should be. So, yep, so this becomes -1 minus 4. So we get -5. Oops, sorry, happened here. So we get here -5. And then 1 minus 4, -3. So we get here -5 is less than x minus 2 is less than -3. For this one, we choose -5 because it will produce a bigger interval instead of having -3, x minus 2 less than 3. Okay, so this is equivalent to absolute value of x minus 2 is less than 5. So going back to our scratch work, we have this original statement from the previous one, this one here, or this one here. So if we now replace absolute value of x minus 2 by 5, we have to add this restriction. So absolute value of x plus 2 is less than epsilon over 5. So we'll also take delta to be equal to epsilon over 5. So here's our formal proof. Let epsilon to be positive and let delta be equal to the minimum between 1 and epsilon over 5. If absolute value of x plus 2 is less than 0, less than delta, which is less than 1, then absolute value of x plus 2 is less than 1. And then we expand this absolute value. X plus 2 is between negative 1 and 1. So this one should be negative 5 and negative 3. Sorry about this one. And then the next line would be the one that we just had solved a while ago. So it implies x minus 2 is between negative 5 and 5. So this is absolute value of x minus 2 is less than 5. And then we take the other delta. If absolute value of x plus 2 is less than 0, but less than delta, which is now equal to epsilon over 5, then we have this inequality. Cross multiplying, we get here 5 times absolute value of x plus 2 is less than epsilon. And we go back to this one here. Let's multiply x plus 2 to both sides. So we get here, this one is less than absolute value of 5x plus 2, which is less than epsilon. And so we have here absolute value of x squared minus 4 is less than epsilon, which we can write as absolute value of x squared minus 4 minus 0 is less than epsilon. Therefore, the limit of x squared minus 4 as x approaches negative 2 is 0. Okay, let's have this last one. Prove using the formal definition of a limit that the limit of x squared minus 16 as x approaches 5 is equal to 9. So we have to scratch work, let epsilon to be positive. So we write it as x squared minus 16 minus 9 is less than epsilon if absolute value of x minus 5 is less than 0, but greater than 0, but less than delta. And then we simplify. Absolute value of x squared minus 25 is less than epsilon, yet it still have the same condition. Then we factor out x squared minus 25 and obtain absolute value of x minus 5 times absolute value of x plus 5 is less than epsilon. We make the same restriction, let delta be less than 1. So the first thing that we do is if we take again this condition and then we restrict delta to be less than 1. So we have this inequality again, absolute value of x minus 5 is less than 1, which means x minus 5 is between negative 1 and 1. We add, the goal here is to produce absolute value of x plus 5. So we add x plus 5 minus 5 minus 5. So we have here x plus 5 minus 10 is between negative 1 and 1. Transposing 10 to both sides, we get here x plus 5 is between 9 and 11. So we choose here 11. And so x plus 5 is between negative 11 and 11. So absolute value of x plus 5 is less than 11. So going back to our scratch work, we have the same, well, we have the same computations. This time we now take delta to be epsilon over 11, and we arrive at our proof. Let epsilon be positive and let delta be the minimum between 1 and epsilon over 11. So the first thing we do is the first part of the statement, delta is less than 1. And then we proceed again in the same manner. And then the next one, we take delta to be equal to epsilon over 11. Now for this one here, notice, after we cross multiply, we again combine this 2 here to obtain absolute value of x plus 5 times absolute value of x minus 5 is less than 11 times absolute value of x minus 5 less than 11, or less than epsilon rather. And then we combine these two to obtain absolute value of x squared minus 25 less than epsilon. But remember, the goal here is to prove that x squared minus 16 is equal to 9. So we just bring back 16 and or bring out 16 and 9. So x squared minus 16 minus 9 is less than epsilon. Therefore, the limit of x squared minus 16 as x approaches 5 is equal to 9. So there's another step involved here. That's all.